Hi guys, welcome you all to my channel Explore Edu to Teach.
So the next topic that we'll be learning in this class will be about Fermi energy level. Already some basic terminology of this subject, electronic devices and circuit, has been uploaded on my YouTube channel EDC playlist. Please go and watch it from there. This terminologies will be frequently used in the future topics as well of this subject, so please make a note of it. And also on my Instagram page there are formula sheets and everything uploaded, some shortcut tricks which will be helpful for you in your time of your exam for your quick revision. So the links of my Instagram page is given down in the description box. If you like the page, please follow me on Instagram as well. So let's begin up with today's topic, that is Fermi energy level. So what do you understand by Fermi energy level? Fermi energy level is the highest energy level that an electron can occupy at an absolute zero temperature. So if I talk about Fermi energy level is nothing else than the highest energy level of an electron that it can occupy at zero temperature. It is very important for you to understand this thing. Fermi energy level is nothing else than the highest energy level that an electron can occupy at zero temperature. So in case of your intrinsic semiconductor, we have discussed intrinsic semiconductor in the last class. The intrinsic semiconductor concentration is given as Ni is equal to N is equal to P. That is, in case of your intrinsic semiconductor, the intrinsic concentration is equal to the number of electron is equal to the number of hole. Then we have the Fermi energy level. Now in case of my energy band diagram, I have the conduction band with EC, I have the valence band as EV, and I have the Fermi energy level of intrinsic conductor given as EFI, and it is drawn at the center. So you should understand this thing. Intrinsic semiconductor has intrinsic concentration equal to N is equal to P, and the intrinsic Fermi energy level will always be at the center of the energy gap between EC and EV. In case of your N-type semiconductor, we have spoken about the N-type semiconductor in the last class also. If you don't know about this, please go and watch it from there. In case of N-type semiconductor, I told you electrons play a very important role. They are majority charge carriers. So you have the conduction band, you have the valence band, you have the EC, you have the EV. As I told you, there is something called as the EFI, which is present over here at the center. But because of the electrons being the majority carrier concentration, which is told as the dopant atoms, the EFN lies near to the EC. Okay, so there is an additional energy level given as EFN, which lies near to EC. It is closer to the conduction band in terms of your N-type semiconductor. Now the electrons which are ideally present in an intrinsic semiconductor also, which I told you, is equal to Nd over here, which is the dopant concentration. So as the doping increases, the Fermi energy level moves upward. So if you see over here, in case of your energy band diagram, you have your EC, you have your EV, you have your EFI as well. So the EFN which is there, right, the EFN will be closer towards my EC, towards my conduction band. Now the EFN minus EFI, if you talk about this, the difference between this, the EFN, that is the energy level because of dopant atoms, that is the majority charge carriers electron, and the intrinsic Fermi energy level is given as Kt by Q ln of Nd by Ni, where Nd is the majority carrier concentration and Ni is the intrinsic carrier concentration. Next you have your P type of semiconductor. So what happens in a P type of semiconductor? Again you have the conduction band, you will have the valence band, you have the EC present over here, you have the EV present over here, and you have the EFI, that is the intrinsic carrier concentration. Now in P type of semiconductor, like in case of your N type semiconductor, you had EFN, right, which was closer to the conduction band. In case of your P type semiconductor, you have EFP, because P is the acceptor atom, that is holes over here. In case of my n-type semiconductor, my dopant atoms, that is my electrons, by the majority carrier concentration. Whereas in case of your p-type semiconductor, it is EFP, that is the holes are the majority charge carriers, and they are closer to the EV, not the EC. So know these diagrams very well. In case of your intrinsic semiconductor, wherein the electrons and holes were same, no one was majority, no one was minority. I had EC, I had EV, I have EFI. Whereas in case of your n-type semiconductor, you have the same energy levels, but you have an additional energy level EFN, wherein EFN is because of the dopant atoms, that is electrons being the majority carrier charge carriers over here. And the difference between this EFN and EFI is given in the formula. Please remember this formula. The notes are present down in the description box as well. So check it from there. You have KT by Q into ln of Nd by Ni. Similarly, for a p-type semiconductor, you have EC, you have EV, you have EFI, and you have EFP. Okay, this EFP is basically the energy level, Fermi energy level, because of acceptor atoms. And the EFI minus EFP is equal to KT by Q into ln of Na by Ni. Like in case of your n-type, you had Nd by Ni, the donor concentration. Similarly, here your Na by Ni, the Ni is the intrinsic concentration and the Na is the acceptor concentration. I hope I am very clear. So you should know how to define a Fermi energy level. These are very much theoretical and basic understanding questions which can be framed in the paper. That is, draw the energy band diagram for an intrinsic semiconductor, for an n-type semiconductor, and for a p-type semiconductor. I hope I am very clear over here. Okay. So after this, let's try to understand the Fermi-Dirac distribution. So talking about the Fermi-Dirac distribution, what does this distribution talk about? It gives the probability of finding an electron in an energy state E. So if my equation says f of E is equal to 1 upon 1 plus e raised to E minus EF by KT, the probability of finding the electron at this E energy level is called as the Fermi-Dirac distribution. So the Fermi-Dirac distribution is basically the probability of finding an electron at an energy state E. I hope I am very clear. So EF is basically the Fermi level. K is the Boltzmann constant, that is 1.38 into 10 raised to minus 23 joules per Kelvin. T is the temperature in Kelvin. And if your E is equal to EF, I repeat myself, if your E is equal to EF, in that case the probability becomes equal to 50%. I hope I am very clear. So just it's a normal calculation, to be honest. If your E value is equal to EF, right? E is equal to EF, then my F of E becomes equal to 50%. Hence the probability of finding an electron at a Fermi energy level EFI, right, when E is equal to EF, will be 50%. Okay. Now you should know this formula again. See, there are some very important formulas which are present in EDC. They are little tricky, little longer to remember, but you have to remember those because numericals will be straight away been asked on this only. The next class will be solving a numerical also. So please hit the bell icon so that you get notified when the new video will go live. So these formulas will be used in order to solve the numericals. How are you going to apply these formulas on the numericals will be learned in that class. All these formulas are written in a crisp way on my Instagram page also. I am trying my best to put it in a crisp way in a sheet and upload it on Instagram so that it becomes handy for you at the time of your examination. And if you just scroll through my Instagram page, all the formulas will be available to you for the quick revision. So please, the links are given down in the description box of my Instagram page. Check it, copy it and follow me on Instagram if you like the page. Now the formula says Nd is equal to Nc e raised to minus of Ec minus EFI by Kt. Okay, the Nd is the dopant concentration, Nc is basically the effective density of states in conduction band, right? Similarly, you have Na. The Na is equal to Nv e raised to minus of EFI minus EV by kT. Na is the acceptor concentration. Nv is the effective density of states in the valence band. EFI is basically the intrinsic Fermi energy level. EV is the valence band, and kT is nothing else. K is the Boltzmann's constant and T is the temperature. So as I told you, in case of your intrinsic semiconductor, the Ni is equal to N is equal to P. That means Nd is equal to Nc, right? The N stands for Nd, the P stands for Nc. So just equate the formulas which is given over here for Nd and for, sorry, it should be Na, right? It should be Na, it should not be Nc. I'm sorry for the mistake over here. It should be Na. So the Nd stands for the donor concentration and the Na stands for the acceptor concentration. The formulas have to be just equated. Take the log on both the sides, the basic formula, and you get EFI is equal to EC plus EV by 2. So this is the basic formula for the Fermi energy level in intrinsic semiconductor. Okay, what I told you, in the next class we'll be solving these numericals which are present over here. So please do watch the next class also, because in the examination these formulas won't be just directly asked, they will be asked in the form of numericals. So you should know how to apply this formula in the numerical. I humbly request you, I have made an effort to make you understand these formulas. I'll be uploading these formulas in a crisp manner on my Instagram page also. You can just follow me on Instagram for a quick revision of all your formulas during the time of your exam and otherwise as well. If you feel that I should make any sort of improvement or any more videos which will help you to remember the formulas very well, or something more should be uploaded on Instagram page, please do comment down in the comment section. So if you like this video, do not forget to like, share, subscribe to my YouTube channel, follow me on Instagram. Thank you so much.